In this problem, we're given the graph of the sine function, and we are to use that graph to evaluate three different limits. The first of which is the limit of the sine function as x approaches 0. Now, for the limit of the function as x approaches 0 to exist, the function does not need to be defined at x equals 0, it just happens to be defined in this particular example. What must happen for the limit to exist is that when you take the limit as x approaches 0 from the right-hand side, that limit must exist. It's also the case that the limit as x approaches 0 from the left side must exist. And then lastly, those two limits that exist must be equal to each other. If those three conditions are met, then the limit does exist. And in fact, I'm sure it's going to be 0 here. So for example, just graphically, when you look at the limit as x approaches 0 from the right, or sometimes I say the positive side, you could think of it as on the real number line, we have 0 here, and you're going to plug in x values starting on the positive side of the real number line, like say 1, and then 0.1, and then maybe 0.01, and you're going to get closer and closer to the value of 0 using positive numbers. So if you did that, say plug in pi over 2, and then maybe pi fourths, etc., you would see that your y values start out to be 1, and then a little bit less than 1, and as your x values get closer and closer to 0 from the positive side or from the right side of 0, your y values are decreasing, because I'm tracing to the left here, and they're getting smaller and smaller and smaller, and you can see that they approach 0. If you were to zoom in really close, you would see as you plug in successively smaller positive values really close to 0, that the y values get closer and closer to 0. So what that means is the limit as x approaches 0 from the right-hand side is the number 0. And then you repeat this and you argue that that also happens as you approach 0 from the negative side. So approaching from the negative side would be like plugging in -1, -0.1, etc. You're tracing to the right, but you're starting with a negative number and approaching the value of 0 from the left side or from the negative side. So for example, if you were to plug in negative pi over 2, you'd have a y value of -1. If you were to move a little bit to the right, closer to x equals 0, then that would give you a point with a y value that's closer yet to 0. It was -1. Now it is closer to 0, and as you trace to the right, you can see that the y values of these points get closer and closer to 0. So both the limit from the right side of 0 and from the left side exist. And what's more, since both of them had the same value, they're both 0, that means that the general limit, meaning not from the right or the left, but just the limit as x approaches 0, is indeed 0. Now the second part of the problem has us evaluating the limit of the function f of x equals sine x as x approaches positive infinity. So on the x-axis, as you move to the right, the x values get larger and larger without bound. You can kind of think of that as it is approaching infinity. Although using the term approaching infinity is a little confusing because you actually don't get closer to infinity. In fact, you never even get halfway there. But you could think of it as x gets larger and larger and grows without bound. What's going to happen to the function values? So this one is a lot like the last one where we start at some value, let's say 0, and we'll plug in successively larger and larger positive x values like pi over 2, pi, 3 pi over 2, 2 pi, etc. And as we move to the right, meaning plugging in larger and larger x values, you see that my y values grow up to a value of 1, and that's the highest value that the sine function takes on. But then after that point, it goes back down to 0 and eventually even goes as low as -1. So the sine function, of course, oscillates between the values 1 and -1 forever to the right, and to the left, in fact. So your y values, your function values, are never going to get closer and closer to any value, or they're not going to, what we say, converge to any value. Like in the last example, the y values got smaller and smaller and closer to 0. We'd say that the function values converge to 0 as x approached 0. So because this function keeps oscillating -1 to 1, -1 to 1, the variation never decreases. From here to here, there's 2 units of variation, and I can do that further in the graph. Right here to here, there's 2 units of variation. So it's important to note in this example that for the limit as x approaches infinity to exist, the variation of the function values must keep decreasing. They must get smaller and smaller, and that's never going to be the case. So because of the way this function is oscillating, the limit does not exist. If you're doing this problem in more, you would answer it by writing D and E, which is just an abbreviation for does not exist. And it turns out that the next example, where x approaches negative infinity, and we ask what happens to the function values, you're going to get the same result, because what happens to the left is the same thing as what happened to the right. If you go to the left, you'll get a y value of -1. Then it'll increase all the way to 0 and then up to +1, still having that 2 units of variation, and that will continue on forever to the left. So as I trace to the left to emulate x approaching -infinity, that limit also does not exist. Now, because I gave you an example of an oscillating function and shown why the limit doesn't exist, you may think that any function that oscillates would have its limits not existing as x approaches infinity and -infinity. So I want to show you that that's not necessarily the case. You have examples where the function continues to oscillate forever, but the limit does exist. So one example like that would be if I define the function f of x equals sine x over x, as it's most commonly written, or you can think of it as 1 over x times sine x. And when I write it that way, you can almost think of the 1 over x, that function, something that can be used to find the amplitude, right? The amplitude would be the absolute value of 1 over x. So what you get is a graph that sort of resembles the sine function. It oscillates, but since 1 over x approaches 0 as x gets large, or I should say x grows without bound, or sometimes we say approaches infinity, you could think of it as the amplitude of the sine function approaches 0, which means it gets smaller and smaller and smaller. So what happens when you see the graph, and we exaggerated it, is it starts up here at 1, and it actually never goes down as far as -1. In fact, it doesn't even get close, and it'll come back up, and because 1 over x gets smaller and smaller as x gets larger, as I trace to the right, the amplitude of the function, or the highs and the lows, will get compressed. You'll have lower highs and higher lows like this. Now the actual graph doesn't quite look like this. I'm just drawing a by hand sketch to give you an idea that if we extended things off to the right, that the amount of variation in the function values decreases. And by the picture at least, it seems like the y values, or the function values, approach 0. Now, not that I've drawn it perfectly, but my point is that even though the function oscillates, you'll get lower and lower highs, and you also get higher and higher lows, and the function values converge to 0. So let me scroll down and show you a more accurate graph of the function 1 over x sine x. And you can see what I said is true. You have a high value of 1 here, and then the high here is much lower, and then the high here is much lower than that. And then with the lows, you have a low right here, and then you have a higher low right here, and that'll keep continuing forever. So it turns out that the limit as x approaches infinity of the function 1 over x sine x seems to be 0. And the difference between this example and the last was that in this example, the variation in the value of the function keeps decreasing forever, meaning this high point to this low point right here has this amount of variation, as indicated by this scribbling that I'm doing, that height. And then from this low to this high, you only have this much variation here. So the variation in function values get smaller and smaller and smaller. Whereas in the last example, that never happened. If you looked at the difference of the highs and the lows, in the last example, your highs always are going to be 1, and your lows are always going to be -1, and there's always 2 units of variation. The variation in the value of the function did not decrease at all. So hopefully those 2 examples show you that when you have an oscillating function, sometimes the limit as x approaches infinity does not exist, and in some other cases, it does.